We start this lecture with an overview, a plan for what will be presented. This pre-lecture introduces an important new concept, potential energy. In particular, for any conservative force, we can define the change in potential energy of an object as minus the work done by this force. In this course, we deal with two conservative forces, gravity and springs. After defining the potential energy associated with each of these forces, we can rewrite the work kinetic energy theorem so that it expresses a conservation law, the conservation of mechanical energy, that applies whenever the only forces that do work in the situation are conservative forces. Last time, we introduced the concept of work as a force acting over some distance, and we showed that the work done on an object will change its kinetic energy. We evaluated the work done by two of the forces we have discussed so far, gravity and springs, and we have found that for these forces, the work done on an object by them depends only on the starting and ending points of the motion and not on the path taken between these points. In general, forces that have the property that the work done by them is independent of the path used to integrate between the 2 points are called conservative forces. If the work done by a force between 2 points is independent of the path, then it must be true that the work done by such a force on a closed path, that is to say, a path that ends up where it started, is zero. Why so, you may ask? Well, consider 2 points, x1 and x2, on the closed path as shown. The work done from x1 to x2 along the top segment must be equal to the work done from x1 to x2 on the bottom segment, since the force is conservative. However, the work done from x1 to x2 on the bottom segment must be equal to minus the work done from x2 to x1 along the bottom segment, since we have just interchanged the endpoints. Now we can see that the work done around the closed loop is equal to the sum of the work done from x1 to x2 along the top segment and the work done from x2 to x1 along the bottom segment. This sum is zero. In general, the work done by a force on an object between 2 points does depend on the path taken by the object between the 2 points. For the special case of conservative forces, we have seen that the work does not depend on the path. Therefore, we can define for conservative forces an associated potential energy that for a given object depends only on its location. In particular, when a conservative force acts on an object as it moves between 2 points, we define the change in potential energy associated with that force as minus the work done by that force between those 2 points. At this point, this definition of potential energy must seem quite arbitrary to you. If we look at this definition in the context of the work kinetic energy theorem, however, it will begin to make some sense. Recall the example from last time in which we applied the work kinetic energy theorem to determine that the speed that a ball, released from rest, attains while sliding down a frictionless surface only depends on the change in height of the ball and not on the details of the surface. In particular, we found that the change in kinetic energy of the ball was equal to the work done by the gravitational force. By our definition, the change in gravitational potential energy is equal to minus the work done by the gravitational force. Consequently, we see that the change in potential energy is just equal to the product of the weight of the ball and the change in the height between the 2 points. Therefore, we see that the change in kinetic energy is just equal to minus the change in potential energy. Whatever kinetic energy the ball gains is exactly equal to the potential energy that the ball loses. If we define the total mechanical energy of an object as the sum of its kinetic and potential energy, then in this case we see that the total mechanical energy of the ball was conserved. That is, at any point during the motion of the ball, the sum of its kinetic energy plus its gravitational potential energy is a constant. On the next slide, we will explore this conservation law in more detail. In the last slide, we discussed an example in which an object's total mechanical energy, the sum of its kinetic energy and potential energy, was constant throughout its motion. We'll now examine the work kinetic energy theorem to determine when mechanical energy is conserved. The work kinetic energy theorem was derived from Newton's second law and states that the change in an object's kinetic energy is equal to the work done by the net force on that object. We can expand the work done by the net force as the sum of the work done by conservative forces and the work done by non-conservative forces. In this course, the only conservative forces we encounter are the gravitational force and the spring force. All other forces, for example, friction, tension, etc., are non-conservative forces. If we now move the work done by conservative forces term to the left-hand side of the equation and apply the definition of potential energy, we can see that the sum of the change in kinetic energy and the change in potential energy is equal to the work done by the non-conservative forces. Now, the sum of the change in kinetic energy and the change in potential energy is defined to be the change in the mechanical energy of the object. Therefore, we see that whenever the work done by non-conservative forces is zero, the change in mechanical energy is zero. That is, the mechanical energy is conserved whenever the work done by all the non-conservative forces is zero. We will encounter many situations in this course in which the work done by the non-conservative forces is zero, which will allow us to apply the conservation of mechanical energy to answer easily many questions that might be difficult to answer using Newton's laws directly. Indeed, the conservation of mechanical energy gives us the relationship between the location of the object and its speed. We'll now do a couple of examples that illustrate the power of this conservation of mechanical energy law. We've defined the change in potential energy as minus the work done by a conservative force between 2 points. We can convert this change in potential energy to a potential energy function defined at any single point by simply choosing some specific point as the zero of potential energy. For example, we can define the gravitational potential energy of a mass m near the surface of the Earth as simply mgh, where h is the height of the mass above a convenient but arbitrary point which we can choose to be the zero of potential energy. For example, the floor, the table, or whatever height seems appropriate. The table shows the form of the potential energy function for all conservative forces we will deal with in this course. The arbitrary constant u0 appears in the general form for the potential energy function, since it will always cancel when we calculate the physically significant change in potential energy. Let's now do an example using the potential energy associated with the universal gravitational force. Suppose we release a ball from a spot far from the Earth and want to know how fast it will be moving when it finally gets here. If the ball is released from rest and has a speed v sub f when it reaches the Earth, then the change in its kinetic energy is simply equal to 1/2 m v sub f squared. Now, the change in its potential energy can be found using the expression shown in the table. Since the initial distance is far from the Earth, we can approximate 1 over the initial distance as 0. What is the final distance? Well, when we discussed the application of Newton's universal gravitational force law between an object and the Earth, we said that we could consider all of the mass of the Earth to be located at its center. Therefore, the final distance here must be equal to the radius of the Earth. Applying the conservation of mechanical energy, we obtain the result shown, that the final speed is proportional to the square root of the ratio of the mass of the Earth to its radius. It is not too hard to see that we would have arrived at exactly the same answer if we had started by asking another very interesting question. What is the initial speed we need to launch something with from the surface of the Earth so that it never returns? In other words, after being launched from the Earth, the object slows down and eventually stops when it is infinitely far away. This speed is called the Earth's escape velocity, and when you plug in the numbers, you find that it is about 11,200 meters per second. We have already derived an expression for the change in potential energy of a spring. If we choose x0 to be 0, we obtain a simple parabola centered on the origin. Suppose we now hang a spring vertically. As long as we assume the spring is massless, it will have the same equilibrium length as before, and the equation for its change in potential energy will have exactly the same form as long as we choose y0 to be 0. So far, so good. Now, suppose we hang a box of mass m on the end of the spring. This will move the equilibrium position of the system downward to the point where the upward force of the spring balances the weight of the box. The amazing thing is that the total change in potential energy of the system due to the spring and to gravity combined still has the same simple parabolic form as before, as long as we make our measurements relative to the new equilibrium position y sub b. We will now prove this claim. Call the displacement from the new equilibrium position y prime. We can now write down the expression for the change in potential energy as we move a distance y prime from the equilibrium position and simplify it to obtain two terms. The first term is just plus 1/2 k y prime squared, which is what we want. The second term is actually equal to minus the change in potential energy due to gravity, since the magnitude of the force exerted by the spring, k times y sub b, is just equal to the weight of the box, mg. Therefore, if we move this second term to the left-hand side of the equation, we obtain the expression shown, that the sum of the change in the potential energy due to the spring and the change in the potential energy due to gravity, in other words, the change in the total potential energy of the system, is just equal to plus 1/2 k y prime squared. The beautiful bottom line here is that the change in potential energy of masses hanging from vertical springs have the same simple formula as masses attached to horizontal springs, just as long as we measure the length of the spring relative to its equilibrium length in both cases. We will close this pre-lecture with a brief discussion of non-conservative forces in the context of the work kinetic energy theorem and potential energy. Here we see a box being pulled up a ramp through a displacement delta x. The forces acting are the weight, the tension, the normal force, and the kinetic friction force. If we write down the work kinetic energy theorem applied to the box as a single rigid object and expand the work done by the net force as the sum of the works done by the individual forces, we obtain the expression shown. The only conservative force acting is the weight. We can bring its term to the left-hand side of the equation and call it the change in potential energy. The left-hand side of the equation is now the change in the total mechanical energy of the box. The right-hand side of the equation is the sum of the work done by the non-conservative forces. It's clear now that the work done by the non-conservative forces on an object is the thing that changes the total mechanical energy of an object. No potential energy can be associated with a non-conservative force because the work it does depends not only on the endpoints of the movement, but also on the exact path taken. Next time, we will discuss in detail the calculation of the work done by non-conservative forces, especially friction, that is responsible for the change in the mechanical energy of an object. We conclude with a brief discussion of the main points of this pre-lecture. First, we define the change in potential energy that is associated with a specific conservative force as an object moves between two locations as minus the work done by that force between those two locations. A potential energy function can then be defined for that object and the particular force by choosing a specific location as the zero of that function. Second, we define the mechanical energy of an object as the sum of its kinetic and potential energies. We then reformulated the work kinetic energy theorem as a conservation law, namely, whenever the work done by non-conservative forces on an object is zero, the mechanical energy of that object is conserved.